Hello and welcome everybody to our colloquium series. Our speaker today is Carla Ramsdell, who is from the Department of Physics here at Appalachian State. The topic of the talk today is food physics, so that's exciting. Cooking up a global climate change solution. I'll hand it over to you, Carla.
Thank you. Yeah, it's a pleasure to be here. I wish we were in the same room together. If you're joining late or just joining, I was just saying, if we were doing this live, I'd be cooking for you too. So hopefully we will be able to do that come fall. So this is me. I am a registered professional engineer. So I just wanted to talk for a moment or two about my path that's led me to food physics, which is something I definitely couldn't have envisioned when I was a student for sure. So my point is that career paths are rarely linear. So it's always hard to sort of envision where we're headed, but I just wanted to run through my path really briefly. So my bachelor's degree is in physics from Stetson University in Florida. From there, I went to the University of Florida and I got a master's degree in mechanical engineering. I am the pre-engineering advisor. So if anybody's on this call that's interested in a career in engineering, please reach out to me. I'd be happy to talk with you about pathways to make that happen. From there, I went to work for Westinghouse Power Generation as a design and test thermodynamic engineer in basically fossil fuel burning, carbon dioxide belching power plant equipment, which is pretty funny. So because now I'm pretty much on the other end of that. So, but it was a great career for a bit. My husband then took a job here at Appalachian State, and so we moved to Boone, and I became an engineer for a smaller HVAC design company that did small commercial and large residential heating, ventilation, and air conditioning design. So from there, I then decided to answer that call finally that I had for a long time, which is why I got my bachelor's degree to begin with, to become a professor. So I became an adjunct professor first, and then now I'm a practitioner in residence here at Appalachian State University. I started out doing a lot of my teaching based on energy, but now I have sort of moved into the study of the thermodynamics of food, which sort of has brought me full circle back into the physics classroom. So you can see by this path that I could have never predicted I'd be a food physicist when I graduated from Stetson many, many years ago. So as far as my teaching journey is concerned, when I started teaching here, it seemed logical I'd be teaching energy since that was my background and that's where I started. I still teach a course 1830, which is the physics of energy and sustainability. But I did notice that in my classroom, when I would interject information about why we cook pizza on a pizza stone, for example, that I would have a lot more engagement from my students about this content. And so based on that, I started sort of teaching more and more about the thermodynamics of food, a bit apologetically in the beginning, because as an environmental steward, I felt like teaching renewable energy was more important. But as I've really research more about the energy of our food system, I realized there's really no apologies necessary. The food system is underrepresented in our both mitigation and adaptation for climate change. So now I really work exclusively trying to connect the food system to climate change. Food is energy. So as a physicist, this is definitely a pertinent topic, and how we manage this energy resource is just as critical as how we manage our fossil fuel and solar and wind and other energy resources. I always like to make sure everybody's on the same page. I imagine this audience we are, but this is a graph. I am such a geek with this stuff. I actually carry a laminated version of this around in my purse, no joke. So it talks about the carbon dioxide atmospheric concentrations over the last 800,000 years. That's the blue line and the left-hand y-axis. So we can see that over the last 800,000 years, we've never bridged 300 parts per million. Homo erectus, us showed up about 250,000 years. I'm sorry, Homo sapien showed up about 250,000 years ago. And you can see within our whole species existence, we've never had carbon dioxide emissions over 300. And today's value is up clearly over 400 parts per million. So there's a normal fluctuation to CO2 in the atmosphere, but where we are today has nothing to do with that normal fluctuation, we can see. The other thing I love about this graph is on the right-hand y-axis, the red line shows the temperature of the Earth's surface. So we also see a really clear coupling between atmospheric carbon dioxide and global surface temperature. So I think this single image just tells a whole bunch, and maybe every human on the face of the planet should see it. So as far as explaining food physics, I decided to focus on 3 different examples of some of the work that I am currently involved with, which links food and physics together. I'm going to spend most of my time on this, which is a thermodynamic analysis of skillet materials using infrared thermography. This was a study, it's published, so I'll share this PowerPoint also, if that's something you do, and then you can click on these. All the images on this PowerPoint are linkable to their source, so you're welcome to seriously geek out about cast iron skillets and read this entire article if you'd like. This was a collaboration with my husband, who's a faculty member in sustainable tech in the built environment, who's also happens to be on this call. So he's a material scientist and a thermodynamicist as well. So we just wanted to dive into this. This was sort of, I took this on because as I started doing this work, I started quizzing people about what their favorite skillet material was. And a lot of people mentioned cast iron, and this wasn't part of my repertoire at that point. But then when I looked up the thermodynamic properties, cast iron doesn't stand out immediately as something that would be an amazing choice. And so this made me curious. And additionally, some people would say, well, I've tried cast iron, but I don't like it because everything always burns, right? Everything burns and I don't know how to manage it. And so as a scientist who was trying to reduce the energy of the food system, this sounded like just really good news. For some reason, apparently, the cast iron skillet required less energy to accomplish the same cooking, but I couldn't explain it on thermodynamic properties alone, so decided to dig deeper. So one question we could ask is, why did we choose to focus on a skillet when there's all these different cooking vessel options? And really, when we're looking at a skillet, typically the skillet is the thermodynamically dominant feature, right? Usually you put a little piece of food in a large skillet. And so the material of that skillet really dictates the success of the cooking. When you compare that to, say, a big crock, like something like this, where you have soup in it, you have so much food. So the food to pan ratio is much higher. We all know that the specific heat of water is off the charts high. So once you add that huge thermal mass, doesn't really matter what cookware you're using. At that point, that vessel is just containing the fluid, not necessarily all that dominant of a factor in the cooking experience. So because of that, also with like oven cookware, you put that sheet in an oven and the whole oven is 350 degrees. So also the cookware in an oven isn't quite as important a material selection as a skillet. So I would argue that really, if you're trying to really have a vessel where the thermodynamics of the material really matters, the skillet would be the most important one to choose. And that's what we decided to do. If you've ever gone shopping for skillets, though, the choices are daunting. There's a ridiculous amount of skillet materials to pick from, right? So you get all different nonstick, and every year somebody else has some new eco-friendly nonstick surface. They're all just chemicals put on top of a metal to make it sound eco-friendly. Stainless steel all clad is definitely a tried and true. There's solid copper, there's enameled cast iron, and there's carbon steel, and then kind of this tried and true cast iron, which are, is cookware that's been in the Appalachian region for a very long time. So let me run through the skillets that we studied in the order that they'll be represented in the infrared images, so we can kind of get comfortable with this range. Obviously, in this length of a talk, I'm not going to have time to really dive deep into all the different findings and all the different skillets. So we're going to focus really on 2 specifically. So we looked at a new cast iron skillet and an antique cast iron skillet. The biggest difference there is that they used to make cast iron skillets thinner and cleanly polished. So they're less hefty a little bit, and then also smooth surface. I also tested 2 carbon steel pans. One of them is a thick French brand that's pretty reflective, and the other is a Lodge. It's thinner and blackened, so it has a higher emissivity, which we'll talk about in a moment. Then we also looked at enameled cast iron pans that we enameled cast iron to drop their reactivity with the food. So if you're cooking something like a tomato sauce, which is going to cook for 8 hours, it's the one thing you probably don't want to do in a cast iron skillet that's not enameled, because you will have too much reactivity between the iron and the pan and the food. Solid copper, I tested a solid copper pan. This thing is just phenomenally beautiful, and the sort of the love affair ends there. Thermodynamically, we were not that impressed with this. It's has a stainless steel coating because copper is very reactive with food, and so you have to make sure. They used to tin them, but they had to be retinned, and now we just coat it with stainless steel. Stainless steel all clad, so you take 2 layers of stainless steel and sandwich in some of these other materials, usually aluminum and copper, to enhance their thermal conductivity. And then last, we tested an anodized aluminum pan. So as I said, so the range, first of all, in price was really impressive. So the cast iron skillet, these are all 10-inch skillets. That's what we tested in all of them. The cast iron runs about $15 new. That beautiful solid copper pan from France cost $200 for a 10-inch and $400 for a 12-inch. So huge range in cost. So again, as I said, we're going to just stay focused on sort of the 2 corners of this. I kept all the images there because they're really interesting to look at, but just to try to focus our conversation, we're going to look at the new cast iron versus the anodized aluminum. And I'll explain why I choose to sort of focus on just those 2. So let's talk about what factors influence the performance and the sustainability of a skillet. So anybody want to, let's just be casual here. Let's unmute yourself and tell me what thermodynamic factors are probably important in in choosing a skillet.
Specific heat.
Specific heat, absolutely. Yeah, thermal sluggishness, that's a big factor, and we'll talk about that.
Conductivity.
Conductivity, for sure, thermal conductivity, definitely.
How much it sticks.
Yeah, great. So how we have a nonstick surface, that's right. That's less thermodynamics, more chemistry, but we can touch on that for sure.
The method of heating.
The method of heating, yes, great. So does it work on just on a resistance cooktop? Can we put it on a flame, on a gas? Does it work for induction? Definitely another really good factor.
Longevity.
Okay, both of those are good. So emissivity is really important. We're going to talk about that here. So how good does this material emit infrared radiation? And I heard the other one, longevity, right? So we're talking about anything sustainability related. We need to talk about the longevity. Cast iron skillets are passed down for generations, right? Which is really great. You don't really hear that about a nonstick. In fact, I love going to thrift stores, and it's always interesting to look at the what's available. Never see a cast iron skillet almost, but always see like stacks of nonstick that are all peeled and nasty. So you can tell that the longevity of those is not quite as great for sure. Okay, anybody else have any final thoughts there? I think we've hit most of them. So yeah, I think conductivity, emissivity, specific heat. We also can talk about the embodied energy. So how much does it take to mine and to, transport and to make these pans from their raw material? There's a pretty big range there as well. We talked about the range of burner options, from a resistance to a halogen to a induction cooktop and gas, the reactivity, which is why we would want to put some kind of non-stick service on it, longevity, and then how easy is it to clean. We can also talk about how beautiful is it, how much do you look forward to coming home and cooking something on here too. So for this discussion, I'm just going to focus on those thermal pieces, right? So for one, thermal conductivity. So here's a range of the thermal conductivity, that K value, right, which talks about how well does this material move thermal energy around. We see clearly copper, that expensive pan, is there because of its high thermal conductivity. Aluminum is next on the list, and you see cast iron, really not so impressive. This is one of the things that when I started hearing people love cast iron, I couldn't reconcile. Like, why do you love cast iron so much? It's a terrible thermal conductor. Carbon steel and cast iron, very similar in their thermal properties. And then stainless steel, I listed only stainless steel's thermal conductivity, although most stainless steel pans have a cladding in the middle that's usually aluminum and copper. So in reality, most all clad pans are much higher than that. Okay, so again, we're focused on these two. I want to keep us focused on this cast iron, which is in the upper left corner, and then aluminum, which is on the bottom right. We see a very significant difference in thermal conductivity between these two. The next thing that somebody brought up was specific heat. Definitely, this is thermal sluggishness. This is how much energy do I have to add to this material to change its temperature? We see aluminum here is the clear winner. Aluminum is very thermally sluggish, but note that this is specific heat and not heat capacity. Right, so we're looking at a skillet specifically. We know the mass of that object, and that has a huge influence on its thermal sluggishness. So it's probably more appropriate when we talk about skillets to talk about heat capacity rather than specific heat. So here we're focused on these two again and look at how different they are. But once I take the mass into consideration, right, note that specific heat's units are joule per kilogram degrees Celsius. I'm now going to multiply that C by M to get rid of the kilogram and talk about it for the skillet itself. What we see here, and I kept specific heat here just for a reference, but we see that again, our two pans that we're focused on, cast iron and the anodized aluminum, come in very close to each other. So while aluminum had a much higher specific heat, it's much lighter weight. And so that additional mass of the cast iron actually kind of puts them on a pretty level playing field. So heat capacity is not going to be one of the big things that's going to influence these two pans' performance. The last thing I wanted to bring up was emissivity. And again, that's how well this material is at radiating its thermal energy. And we see that, that cast iron and anodized aluminum are very similar. In our studies with the infrared thermographer, we put actually high emissivity tape on these pans and took pictures of them to verify that if the tape is basically invisible, then we know the emissivity of the pans are good, and we can rely on the results that we're getting from those. Okay, so this sort of summarizes what I've just talked about. And what we see here is that based on what we just brought up, of the thermal factors that we're considering, thermal conductivity, heat capacity, and emissivity, the real difference between these two pans is in their thermal conductivity. Okay. We use an infrared thermographer. This is a FLIR camera, and it's a special one that has high temperature capability. A lot of FLIR cameras stop at around the 200-degree Fahrenheit range, looking at skillets that are going up to about 500 degrees, so we needed something to go higher. Infrared thermography, I think all of you on this call probably realize this, but it's based on looking at the wavelength signature of what's being emitted from the object, understanding that hotter objects emit shorter wavelength than colder objects. And so this has a whole matrix of those sensors. It converts that wavelength to a temperature and then to a color. So it actually allows us to see in the infrared region, which is where our cooking happens, right? So this is the small little slice of our visible spectrum that our eyes, the rods and cones in our eyes, can detect. Most of our heating occurs at a longer wavelength than the longest wavelength we can see. And so infrared thermography gives us kind of superhero powers that we can see into that range, which is pretty cool. Here's a picture of me cooking, so we can see clearly we have a temperature scale over here, the very hot skillet being on the high end, and these other ones being cool. If you've never played with a FLIR camera before, you really should. They're crazy fun. One of the issues we had with this research was because we were dealing with a wide range of pans with different emissivities, some very low, meaning they're very reflective, and some high, we couldn't always trust the results of the infrared image. And so you can see a picture here, for example, of that stainless steel pan. This block in there is truly just masking tape, which has an emissivity close to 0.95, pretty close to it, the same as cast iron. So we can see that the masking tape actually gave a valid reading of the temperature, but if we left the pan shiny and uncoated, we couldn't rely on that result. It is not this cold, it's actually this temperature. And so you'll see in some of the images some stripes, and those stripes are genuinely this high emissivity tape that was put on there so that we could accurately compare the different results. Okay. So here is the graph of our results. And what I'm showing here are on the x-axis, we have heating time. So we took each skillet and put it on a burner with a 400 watts of power electric. This was just an electric resistance burner. And we looked over time at what the hottest spot on the skillet was, right? So the FLIR allows you to pick a hot spot, and within a sort of a box that it was looking at, it chose the hot spot. So that's what this is. This is the maximum temperature at the bottom of the skillet in degrees Fahrenheit over time. Right, so again, what we're going to focus on is this green line, which is the anodized aluminum, and this black line, which is the new cast iron. Right, and I think this is pretty counterintuitive. If we look at, for example, at the 5-minute mark, we see that highly conductive anodized aluminum has a lower temperature than the cast iron. This doesn't sound right. So I'm even more confused now, right? I was already confused that people love cast iron. I couldn't justify it by its thermal properties. And now I was even more confused. So it really took infrared thermography for us to be able to really see what was happening there and why that might be the case. Okay, so let's head on now to our images. So this is how the images are all going to look. Again, what we're looking at is this top box with the new cast iron and the bottom box with the anodized aluminum. This is heating. I can't see my whole slide. After a minute, I believe, or 30 seconds. How do I get rid of you all? Go away. Hold on just a minute. There we go. Oh, this is heating. Sorry, I went ahead too far. Let's go back here. Okay, so this is, here we go. Heating after 1 minute. So we're just going to sort of watch these things heat over time. So this is now heating 1.5 minutes. Here's 2 minutes. Here's 2.5 minutes, 3 minutes, 3.5 minutes, 4 minutes, and 4.5 minutes, and 5 minutes, right? So I'm just going to go back over those for a bit because they're just so darn beautiful to look at. So let's start again at 1 minute, and we're just going to sort of tick through here and see how that thermal energy is distributed. I could watch this stuff for hours because it's so cool. But what we see here is what I was showing in the curve at the 5-minute mark. Again, the same amount of electrical power is being pushed to these pans. We see that the hot spot at the bottom of the cast iron is 408 degrees, where the hot spot in the bottom of the more conductive anodized aluminum is 333 degrees. Anybody want to pick up on anything else that seems pretty dramatically different between these images that may help to explain what's happening here?
Heat distribution.
Oh yeah, 100%. That's exactly right. So the heat, we see what happens on these highly conductive pans is not only does the thermal energy come through the bottom effectively, but it also sheets that thermal energy out to the edge of the pan as well. So we see, even if we back up before, say, 3-minute mark, look at how homogeneous the temperature of this anodized aluminum pan is versus the cast iron, which has really cold edges still, and we still start to see some of these much hotter temperatures at the bottom. In a skillet, I don't really care what the temperature of the edge of the skillet is, right? It's really only there to contain the food in a skillet. It's not true for a pot, but for a skillet, the edge is there so I can flip my pancake up against it. So to me, it seems like now all of a sudden thermal conductivity isn't something we necessarily want for the efficient management of thermal energy in a skillet. I actually want that thermal energy to stay at the bottom of the pan where my food is located. And so perhaps this gives us one of the clues as to why we have these like higher temperatures at the bottom of a cast iron skillet, and why maybe food burnt for people in a cast iron skillet who may have been more familiar with cooking on one of these more conductive skillets, right? Because the temperature here is significantly lower in the same period of time. We looked at a lot of other factors as well. So all the things we spoke about in the beginning were significant. The emissivity was important, especially when we looked at, right, this was looking at the thermal transient during heating. We also looked at thermal transients during cooling. So once it achieved this 500-degree temperature, we took it off the burner and watched it cool down as well. We saw the pans that had the higher emissivity cooled more rapidly. That obviously was a really important interplay between heat capacity and emissivity, but they're better at throwing their energy away by radiation. Also we looked at like steady state conditions then also. So we let them sit on this burner for an hour and looked at what the distribution was when we felt like there was a balance between the energy coming in and the energy being shed. And that gave us some really good highlights as well. So in the end, it really came down to a really complicated interplay between the thermal conductivity, the heat capacity, and the emissivity, which really all came together. When coupled with the longevity and the non-stickness and the reactivity and the embodied energy, it really became clear that cast iron was the champion on almost every one of those metrics. So that was fun, and it was $15. So I love when research sort of throws away the $200 copper skillet for that. So I wanted to just highlight for just a moment something I find really important. I try to make really clear in a lot of my classes, and that's that as scientists, we should probably value communication to non-scientists as much as we do to other scientists. So my work, because there aren't really a whole lot of food physicists in the world, my work is typically communicated to non-scientists. I go to multidisciplinary conferences on food studies, and they always wonder why the heck the physicist is in the room, because I don't seem like I belong. And so I'm always mindful that my communication has to be, really clear, right? So we as physicists love graphs and charts and data and this stuff, right? This makes us really happy. Doesn't make everybody happy. And in fact, people just shut down often when you throw a curve up. And so I just like to mention that because unfortunately, we're still using words like believe in associated with climate change, right? To me, this tells me that probably as scientists, we're not doing a great job communicating science. I think this shows us that a picture is worth 1,000 curves potentially, or graphs. And so maybe we should, always be focused on ways to not only communicate our work to other scientists, which is critical, but also to communicate to the rest of the world as well, so we can bring them along on our journey. Okay, I think I'm going to hold on questions if that's the way this usually runs. Okay, so I'm just going to give you two other examples. These are going to take much less time. One of those is solar cooking technology. So in my lab there in Garwood, I think I'm up to 16 solar ovens, maybe a little out of control, but they keep coming out with these new things that I feel like I must test as an energy efficient cooking person. So I did recently have a cooking demonstration for the College of Arts and Sciences, and this will link you to that video if you want to watch all of them in action. I cooked some Impossible burgers and some potatoes and peppers, and of course some ginger snaps and a cup of cappuccino. So you're welcome to watch that. I just wanted to go through those technologies briefly and talk about the physics there. They're rich with some fantastic physics. There's all different models of solar cooking strategies. These two on the left would replace an oven. They're box oven and evacuated tube ovens. The one on the right is a reflector. That would replace the stovetop or burner. And so we can look at them really generally. A box oven is the least sort of sophisticated. It truly is just a super insulated box with these reflectors. The law of reflection helps those reflectors to funnel more solar energy into the box. The box has a glass surface, which is low iron, low reflectivity, which allows the thermal energy to come in. And then we set up a huge greenhouse effect within the oven, which allows the temperatures there to get to 350 degrees in about 40 minutes or something. So they work really well. This is the small scale. There also have some really large industrial scale or maybe community scale versions of these as well for resource limited environments, which is pretty cool. The reflector sort of works just like that. So that we have this parabolic reflector, which focuses the solar energy onto the pan itself. Actually, some research has shown that in third world countries, these have the highest adoption rates, because from a social standpoint, you're basically just replacing a three-stone fire with this. So all the other cookware and vessels and methods stay the same. So while they're really not very efficient, because wind can completely or mainly wipe out the solar gain and those kind of challenges, if they're being adopted more, then there's something to certainly, to say for that. So here is some of the solar reflectors we have on our campus. The Office of Sustainability has this one set up all the time. This is a portable one. Here I am walking across campus with that portable one on my back. So it's okay. It's not great, to be totally honest, but it's pretty cool because it's portable. If there's no wind, it works really well. Any breeze makes it a pretty big issue. My work is focused really in the evacuated tube. So an evacuated tube is just that, two concentric cylinders. The outer cylinders borosilicate glass, again, low iron, low what's that word? Transmissivity, lets the solar energy in without reflecting. The inner liner is coated with a titanium oxide that does a really great job at absorbing the solar radiation wavelength, but not a good job at radiating the oven's wavelength, right? So, and then the space between those two cylinders is evacuated, so you can't lose thermal energy by conduction or convection, because both of those mechanisms require a medium. So yeah, these are unbelievably efficient. One of the biggest issues with an evacuated tube is actually burning cookies. I burned cookies on that video I just told you about. Very frequently in outreach events, I get talking. Clearly, I do that very well. And my ginger snaps burn, right? So it happens really quickly. I've gotten these things up to 650 degrees inside. They're amazing. So here's a bunch of different examples of solar evacuated tube ovens. Here, I happen to have one here. This is the GoSun little, it's called the GoSun Go. It's a very small oven you could just bring with you to the park or something. It works so amazingly well. Has reflectors in there, and we see that evacuated tube. We can just pull the tray out here, and the tray has these little silicone baking things. Obviously, this is really small, but for one or two people, it does a great job. Hot dogs, peppers and onions, little bread rolls, muffins. I've put little silicone muffin tins all the way down here. So yeah, it works really well, super small and great. We can see this is the latest one I have actually purchased personally, which has a PV. It actually has an electric strip. So this is what's called a hybrid oven that can get thermal energy from the reflectors as well as from an electric strip in the bottom of the pan. So if you had a partly cloudy day, you could still get as much energy as you can from the reflectors, but this can be plugged in either to like a car cigarette adapter or to a solar panel, which or to a battery. It comes with this big battery pack, and that battery pack can be charged by one of their solar panels as well. So, I mean, these could even cook indoors then. You could charge that that battery during the day with that solar panel. And then when you came home, you could then plug the battery into the oven and cook at home, which is pretty ingenious. So one of the big challenges with solar cooking is that we don't do most of our cooking in the middle of the day when the solar access is the greatest. These are all based on the law of reflection. I think we all got this right. So the law of the angle of incidence equals the angle of reflection, true for a flat surface or a curved surface, true for any point along the line. If you just find the tangent of that curve, then the law of reflection still holds. So it may seem intuitive that in order to focus the solar energy onto a point, we would want a circular reflector. But what we know about circular reflectors is that actually the focal point is along a line. This is greatly exaggerated for the purpose of this PowerPoint. But the point is, if my oven is here, a lot of the reflected radiation is going to miss the oven completely. So instead, what we want to do is look at a parabola. And in a parabola, we know that all the reflective rays from the laws of reflection will hit my oven, there's a parabola, the slice of that cone there. And the other important thing is that these actually have to be adjusted frequently. About every 20 minutes, any solar oven needs to be adjusted as our location relative to the sun changes. So if you leave it alone and you have the solar radiation coming in at an angle, we see the radiation also gets skewed and misses the oven completely. So there is some maintenance that has to be accomplished here. The work we're doing right now is we're looking at evacuated tubes as a way not only to provide ovens to resource limited environments, but also to pasteurize water, to bring water to a safe drinking temperature to kill any possible microbes. So most of that is done, as you've seen, by reflectors. We've met with some nonprofits in this area like Wine to Water that are doing a lot of work in the pasteurization of water. And the first thing they said when they saw this really beautiful reflector was that in a resource limited country, those reflectors probably wouldn't stay around very long with the evacuated tubes because they're more valuable as a mirror than they are as a reflector. And so they challenged us to think of ways that we could focus the energy in a way that doesn't involve a shiny surface. And so we are looking now at a Fresnel lens that's a line focus Fresnel rather than a point focus. It's not quite so dangerous. A point focus works really well. There are ovens that use those, but if you get between, if your skin gets between the lens and the cooktop, you can really burn yourself pretty significantly. It's not as big of a concern on a line focus. And because evacuated tubes are this long focal point, right? It makes sense to use a line focus Fresnel lens anyway. So here's our two apparatus. We have this reflector, and then we have this Fresnel lens on a box with a tube inside there. Our results have really been fabulous. I have a student taking final data on this semester, and his results are confirming what we found, that for the most part, actually the reflector is more effective than the lens is actually more effective than the reflector was anyway. So we're pretty jazzed about these findings and hope to publish that in the coming semesters. The last example I wanted to bring up was this food visualization tool. So I teach a couple classes on the physics of food and cooking. Cooking's fun, right? That's a really fun thing to apply thermodynamics to, but it is not, I don't know, I just don't feel right just focusing on the fact that if you cook efficiently, you're going to make a really significant change in the carbon footprint of our food system, because a way bigger determinant is what food you choose to bring home in the first place. The amount of greenhouse gas emissions that are emitted from our food, from the growth and the production and the packaging and the transportation and refrigeration, what it takes to grow that food product and bring it to your home varies greatly in their emissions. The Environmental Working Group publishes this graph in their Meat Eater's Guide, and this shows the equivalent carbon dioxide emissions. So just make sure we all know what that is. If one of these foods like beef, for example, its biggest emission is methane, that's CH4, a much more complex atmospheric molecule. And so for every one methane molecule that's released, it's about as, it has about 25 times more impact on radiating back to the earth as carbon dioxide. So they put it on a sort of equal playing field by making everything in terms of an equivalent carbon dioxide molecule for their impact. So what we see here is that there's a big range in the impact of our food from a greenhouse gas perspective. We also can look at this, which is a free calculator. It's called Clean Metrics, and you can put any food in here, any quantity, any transportation distance, and it will tell you the equivalent carbon dioxide, kilograms of carbon dioxide on there. I think I saw my friend Lila Barrera on here. She is the student involved in this research, and I appreciate her being here for sure. So our question to each other was like, well, that's great, but what the heck does a kilogram of carbon dioxide look like? It's hard to really impact real change if we can't see what that is. And honestly, I'd been involved in this work for years, and I couldn't answer that question. So the dinner I had last night, the emissions, the greenhouse gas emissions that it took to bring that food to my plate did it fill this room? Did it fill a small balloon? I just had no real good visualization of that. So we took on this project together to try to use a tool that can be used both in an educational environment, in an outreach environment, even in a cafeteria or something, to try to inform the public better about their emissions. So for example, if I presented you with these choices, so you pick your dinner. What are you having for dinner tonight, right? And maybe throw it in the chat for me so I can make some determinations on what you're doing. You want some kind of protein. So we have chicken, black beans, hamburger, or salmon. You want to add a carbohydrate to that. So do you want pasta, potato, bread, or rice? And then last, you want to had a vegetable. We should all eat our vegetables. So carrots, spinach, broccoli, or tomato. So if you had to pick one thing from each column, what would you have for dinner tonight? And I'm going to hop over and look at the chats here so I can get some of your answers and start to do a bit of analysis. Yeah, we got a lot of really great options here. So salmon, rice, and spinach. We have chicken. We have, keep coming in here. Think really, you all are such healthy eaters. Okay, here's what I'm gonna eat tonight. I'm gonna eat a hamburger, and I'm a hamburger and rice and broccoli. That's what I'm gonna have for dinner tonight. So I'm gonna stop sharing this for just a moment, and I'm gonna hop over to share another screen with you. So this is, I'm sort of a cooking evangelist is the way I like to call myself. I believe that we have this incredible ability to truly impact the climate by the food that we choose, both in our purchasing dollars to help to lead the food system in a way that's really conscious, and also what we choose to bring into our kitchen and how we cook. And it ends up being healthier anyway. We know there's a lot of evidence out there about how mentally grounding cooking can be as well. It reduces food insecurity because cooking at home is so much less expensive than relying on a processed food system. Here's my shameless plug. I'm teaching a course, PHY 3530, this coming summer, which is the Physics of Food and Cooking, an upper level physics class. It will be online, but everyone taking the class will have laboratory equipment at home. So we'll run cooking labs, compare results. And so definitely reach out to me if you want to talk to me about that. So that's all. Thank you very much. I do have a website with a blog that I try to keep pretty active to help to communicate to people some of these physics and food connections if you're interested in learning more. So thank you so much for your time, and I'm happy to entertain any questions.
Thank you, Carla. It was a really enjoyable talk. I'm a bit sad because all the good food is not healthy for the environment. I'll open the floor for questions. Yes, Jesse, go ahead.
Hey, Jesse, how are you?
Good. How you doing?
I'm great. It's good to see you.
Talk. Super fun and entertaining. Good stuff.
Great, thanks.
I noticed the differences in the thermal conductivity and emissivity among the 3 different cast iron pans, their age. And do you think that's just from like a change in the thickness of them, from them being like worn out with use, and then the thinner ones heated up faster in the middle or something?
Okay, let's go back there.
What's up with that?
Oh, hold on just a moment. Let me go there. So you were talking about, were you talking about emissivity? Oh, you were talking about in the picture itself?
Yeah, the pictures of.
Yeah, I gotcha. Let's go there. So, yeah, so which 2 were you talking about? I'm sorry.
The cast irons with different ages. So the antique versus.
Yeah, really interesting. So let's take this here. So as I said, cast iron, it used to be made differently. So they sand cast it the same way they do now, but they also finished it. So they would, polish it. And in that polishing, it got thinner for one. And so we can kind of see that here after like 3.5 minutes, we see a hotter hot spot at the bottom because it has less thickness to go through. And so that happens much more rapidly. Does that help answer your question?
Yeah, that's great.
Yeah, they're pretty significant. So let's go back. Let's look real quick at like the heat capacity numbers, because that would take the mass, the specific heat of the two are the same because they're both cast iron. But look, the vintage one is here versus the new one, and that's just a factor of the mass because they're thinner.
Gotcha. And for your personal cooking, do you prefer older ones or newer ones, or?
I like the newer ones, to be honest. So that sand finish, like it looks like it would be nicer to have a smoother finish, but the sand texture adds more surface area, and so a seasoning sticks so much better to the newer pans than it does to the older ones. So both carbon steel and antique cast iron lose that seasoning. Unfortunately, that's a terrible word. Seasoning has nothing to do with flavor. It's just that polymerized oil layer that we build up on the pans by getting it through the smoke point, that makes it nonstick. That sticks, is much more resilient on the newer pans because that increased surface area of the texture of those.
Oh, I didn't know that. That's really cool.
Yeah, I didn't either for a while, but it's and it's true. I've tested them. They're very resilient because it has a lot more to grip onto, basically. So, thank you.
Connor.
Hi, thank you for the talk. I thought it was really informative and pretty interesting.
Yeah, thank you.
So my parents recently bought stainless steel, at least we assume they're stainless steel pans. I'm wondering, based on your research, because every time they cook, everything, regardless of what they cook, sticks to the pan. Like they can't figure out why. I'm wondering if with your research, you could kind of explain why that would happen.
So stainless steel, it's great. I do use stainless for a lot of things. That's the one drawback, is you can never make them non-stick, right? So there's no sort of way to lay a seasoning on stainless steel like you can on cast iron. And so the way to really avoid it as much as possible is to preheat the pan first and then put oil on it, allow the oil to preheat, and then cook it. There are different levels of that stainless steel. Some tend to be more, do better about non-sticking. I'm not a material scientist, so my knowledge in this area drops off really quickly, but I do know that's one of the drawbacks of stainless, is that you can never get them to be non-stick. They always start out with just a stainless steel surface. Again, you can't build up that non-stick surface on it. So yeah, I mean, they're great for stock pots and soups and things like that, because you don't have to worry about sticking so much in those situations. But as skillets, I think cast iron's always going to be my choice, probably.
Thank you.
Yeah, sure. They're not reactive. So that's the benefit. If I make like mama's tomato sauce that cooks for like genuinely 12 hours, I'm always going to use a stainless pan because there's no reactivity there.
Forrest Myers.
Thank you for the talk. I had a question about
sure.
the food emission chart. So that showed different values of carbon dioxide for different types of meat. I wondered if those values changed at all for whether the, let's say, chicken was raised by like a big company versus somebody like raising chickens in their backyard. And if they how much.
That's a great question. And yes, so this environmental working group kind of bases it all on industrialized food. But if you go to this clean metrics calculator, they actually allow you to make those finer tuned decisions, right? So you can, for one, you can put in the transportation distance. So that right there, you could see what the difference in transportation. A lot of our meats are not only transported long distances, but once they're slaughtered, they need to stay frozen or refrigerated. That greatly increases the energy of transportation, because you're not only driving it, you're driving it in a huge refrigerator. The refrigeration, that vapor compression cycle is not efficient, right? And so you start thinking of that, and it adds an enormous amount of energy to the transportation. So I don't think any of it's perfect. You ask a really good question. I am actually on the board of Blue Ridge Women in Agriculture. We are, the local foodway basically of the area. There's a online farmers market called the High Country Food Hub that allows you to really increase a lot of your local food. And so I'm a huge fan of promoting local foodways for not only transportation energy, but typically small scale farmers manage a lot of their resources better because their margins are smaller typically. So yeah, it's a really good question, complicated answer. I think this will get you part of the way there, but maybe not answer it perfectly. I'd say local is typically going to be a better choice.
All right. Thank you.
Sure.
Graham?
Thank you for your talk. I want to say it's very inspirational as someone who sustainability is a very important topic, but always trying to link it to what I'm doing is a hard thing. And
Awesome.
seeing food physics and sustainability is really cool.
Great.
But I had a question about the evacuated tubes. I don't know, I couldn't really tell from the pictures or something like that, but I unfortunately know more about vacuums than I ever wanted to. And, I couldn't really tell, does that vacuum extend to the ends of them as well? Because it looks like with the screw top, that might be hard.
Yeah.
There's a lot more, like any loss of heat you would see at the ends or not.
Yeah, I don't know how well you can see this, but basically the edge where you come in and out is just, so this is the inner and outer thickness, right? So it's not a very big gap between them. On the other end of things, right, we have, it's all sealed off. This actually has a little cap, but there's actually like these little metal spacers here, which help to support the inner tube within the outer tube. There's actually a disc there. Oh, what is that? It's like, anybody remember what the material is who happens to be on this call? Like maybe my husband. Can't remember what that. There's a material in here that if the evacuation is broken in this here, that you no longer have a vacuum, it actually fills the space with a white powder so that you know that your vacuum has been compromised.
Okay, that's awesome. Thank you.
I've broken enough of these things to know. If you come by my lab, I have plenty of samples of what that looks like, because that's one of the hugest drawbacks of evacuated tubes, is that they're pretty fragile. This is the second tube in this one, actually. So thankfully they have replacement tubes, pretty economical.
Awesome, thank you.
Yeah, thank you.
Forrest?
Hello,
Hey.
thank you very much for your talk.
Certainly.
So I know that one of the biggest issues in the food industry is how much food we throw away and how much is wasted.
Yes.
And I was curious if you've done any research into that, and if you have any advice on how to get rid of food at your house in a sustainable manner.
Yeah, that's an excellent question. Honestly, I have not done work specifically in this area, but it is an enormous issue. 40% of the food that's grown in the United States is wasted. So if we're talking about the management of an energy resource, to throw away 40% of it just is unexcusable. Honestly, a lot of that, we think about that happening in your refrigerator at home. Most of that happens before it ever leaves the farm. And that's because we are really picky. And they know that if a tomato has a blemish on it, or a potato is misshapen, we won't buy them. We want a potato that looks perfect. And so thankfully there is a movement in this direction to try to open people's possibilities of what a good looking pepper looks like or whatever. But if you look deep into this, you'll see just like piles of yellow squash, for example, that never even left the farm because it wasn't worth them trying to transport that to grocery stores, knowing that in the grocery store it wouldn't be sold. So it's one of the other things I love about local foodways. I pick up stuff from the food hub. It almost never is perfect, but it's beautiful. And that tells me that that stuff is not going to waste in the at the farm itself. We end up having a much larger, consumption of the food that's actually grown. So the food waste thing is a big deal. There's even apps available now where people that have, not in bigger communities than ours, but that have food left over can text to a group and say, hey, I got food left over, and people can come and connect. And there's a lot of work being done in the space that's really encouraging. I'll put it that way.
Thank you.
Yeah, sure. And I think when we talk about food waste, we don't only talk about the waste of the energy, we also talk about the waste of water. So I think if I get this right, like throwing away a half of a hamburger wastes the water equivalent of taking an hour-long shower, right? So it's not just the loss of that energy resource, but everything else that went into it, which is really significant.
Yeah, for those who are following the chat box, Dr. Boris has just shared a link to Misfits Market.
Yeah.
You can find misshaped vegetables there.
Thank you. Yes, absolutely. That's great.
Okay, Lila.
Hey, Carla.
Hello, my friend.
Great talk. I had a question back at the skillet materials. I noticed that in Figure 8, and if you wanted to go back, I think it's slide 17.
Okay.
I noticed that the enameled pan tracks really, really well with the new cast iron. So
Yeah.
like, I don't know if I missed, the enameled, like, can you clarify like what the enamel coating does and like why are they so perfectly tracked?
Yeah. No, I thought that was wonderful data. I was so delighted to get that actually. They completely track on top of each other, which tells me for one that enameled coating does not interfere with the thermal properties of the cast iron, which is great. The only reason we enamel things is to drop their reactivity with the food. So like I said, you build up this polymerized layer on most raw cast iron, which makes it really nonstick. But if you're cooking tomatoes, a highly acidic food for hours and hours, you're going to break down that surface. And so really the only time I would ever see using an enameled cast iron is for those long stews. So like, I don't know why you'd ever get enameled skillet, because most everything you do in a skillet is pretty fast. But in a stock pot, if I'm cooking soup all day, I want that enameled coating there. And I was actually really encouraged to see that those tracked so well. So I think then you could also assume that like the obviously heat capacity, you're not going to mess with it. So a lot of those things we love cast iron about are retained. When you enamel it, you just lose that nonstick ability. Some people are confused with nonstick skillets because when they're enameled, they enamel the inside in black. And that therefore makes it seem like the inside is still that raw cast iron that you could season, and that the outside is enameled just for beauty. But it's not true. If they enamel the outside, they enamel the inside also. They just always do it black, because if they did it another color, it would discolor over time. So even though it looks like the inside of an enameled cast iron skillet is black, it's not seasonable. It's enameled coated.
Gotcha. That makes a lot of sense because I always envisioned the enamel to be the outside portion. So
Yeah.
how does it, I don't know, interfere with the reactivity? Okay, cool.
No, I've looked into all of them because I had the same thing. They're all black, but they are all enameled on the inside as well. So unable to get a nonstick surface on an enameled one, and they cost a ridiculous amount of money too. So, which is always amazing. Those Le Creuset are like $300 or something. They're crazy. So. Stick to the $15 for the most part.
Evan?
Hello. Great
Hey,
talk.
Evan.
Your delivery is really good. And I was just wondering what like your favorite pan material is yourself.
Yeah, let me tell you. So I just happen to have right here by my desk, cast iron. Yeah, so this is funny because this cast iron pan, it says Mass General Store. This was given to us as a gift when we first moved here. This was not part of anything that I cooked on. And actually it sat in a box or in a drawer for like years before I got into this research, because it just wasn't part. I even have a funnier story to tell because my husband's online as well. When we first got married, he got a bunch of cast iron cookware from his family. And I was like, honey, we don't live like this isn't Little House on the Prairie anymore. We don't need to use this cast iron stuff. And so it got sort of bumped like, to the basement and then to the garage. And then it's a true story. It got put in a shed, like up the hill from our house, because I just never used them until I started doing this research. And I was like, that stuff is amazing. So I found myself one night on eBay trying to find a used cast iron skillet. And I was like, oh, wait a second. I got a whole box of this stuff. So I trudge up to the shed in my snow boots. And sure enough, there was like a Wagner in there, all this amazing stuff. So my apologies to my husband, but actually this, cast iron is just, I take this cast iron skillet out every single day to cook on. I mean, that's one thing I'll say about cast iron. You basically need one of them because they like to be used, right? That seasoning will go rancid. So I'm not one of these that has to have a 10-inch or 12-inch and different edges and all these, just one and you're done. This thing comes out every single day. It's amazing. The only drawback is it's heavy. So it's hard to get that pancake and do that flippy thing. I can't do that. It's just too heavy. That'd be the biggest drawback, but you will not be disappointed.
Great. Thank you.
Yeah, sure.
And now it is a little bit like Little House on the Prairie.
Yeah, true. COVID's gotten the best of all of us.
Well, it's past 5 o'clock, so if you have to be somewhere, you can leave. I have a question of my own for
absolutely, please.
For you. So the plot where you had, the temperature versus time for the different skillets,
Yes.
It shows how quickly we can achieve a certain temperature or how quickly it heats up. But typically, when you're cooking, you're looking for a steady state heat.
Mm-hmm.
So which skillet, in your opinion, maintains temperature best for, cooking over a period of 30 or 40 minutes?
Yeah, that's a great question. So that becomes complicated because you have this interplay between, so a cast iron skillet, right? This outer edge is really emitting a lot of its thermal energy. We're talking about skillets here specifically. We actually, within that paper, which I should have up, but I don't have up right now, we have a steady state temperature image as well, which you probably would like to look at. In fact, let's just go there. I think that this link should take me there, so that could be useful because I think this steady state image is going to answer your questions. So let me stop sharing this and now hop over to, can you all see that? Oh, but of course now it's going to go to a PDF. One more time. Okay, can y'all see this?
Mm-hmm.
Okay, perfect. So if we run through this article and get to, now the steady state pictures were difficult because, right, so these are the pictures of steady state. Now, and that's too small, but the same order as before. So what we were trying to see here is what was the interplay between the emissivity and what was coming in to the bottom. Where do we hit a steady state situation, right? And so what became challenging were these low emissivity pans, because if we coated the whole pan with that tape, we were disturbing the results, right? We were basically increasing the emissivity of a pan that wasn't very emittive. I don't think that's the right word, but so instead we just put a single strip of tape so that we could allow the pan to be a poor emitter, which it is naturally, and still see what the temperature distribution looked like from edge to edge. So we actually see that in that situation, when we, again, all these sat there for an hour, and we can see that these pans that are poorer emitters actually got to these hotter temperatures. Also, like for example, this antique cast iron that's thinner got to a higher temperature on the inside. So I don't know if those images help answer your question, but it's pretty interesting to see it in steady state. Does that help?
Yeah, cool. Great. Thank you.
Yeah, sure.
Do we have more questions? If not, let's thank the speaker once again. Thank you for the talk. It was really interesting.
Yeah, thank you for having me. It's a pleasure.
Yes. So have a good weekend, everybody. Goodbye.
Thank you.
Go out and cook something.
Thank you.
Bye-bye.